Hello and welcome to follow my videos. My name is Matti Ylitalo and today our focus is how we can improve heat transfer. Just a second, I'll put the presentation mode on. This is a general level guide how we can improve heat transfer. I took some examples from electronic cooling, heat and ventilation and air conditioning, and some typical industrial heat exchangers. I created this guide with ChatGPT, and as a first solution it pointed out this increased temperature difference. Temperature difference is the driving force in heat transfer, so it always affects a lot. But in practice we typically have those temperatures of our source and our location where we want to move this heat. So we cannot affect on those temperatures. So we need many other methods to increase the heat transfer. One good way to improve heat transfer is that we improve conduction. Conduction means heat transfer through solids. Materials like copper and aluminium have much better thermal conductivity compared to, for example, to steel. And one good way to increase heat transfer is also that we use minimum thickness of conductive materials. And remember always to eliminate air gaps between materials. Use thermal grease, thermal pads, shoulders to ensure that you have good connection between materials. You can increase heat transfer by increasing surface area. More surface area means always higher heat transfer rate. You can add fins, ribs or any kind of extended surface. And a rough surface means always larger surface area. You can also use micro channels or porous materials. You can also enhance convection. Convection means heat transfer between a surface and a moving fluid. If you are working with air, you can add a fan to increase the velocity of your air. And if you are working with liquid, for example with water, you can add a pump to increase the velocity of your water. You can also affect on turbulence behavior. The more you have turbulence, the higher is the heat transfer rate. And typically with liquids you get better heat transfer compared to gases. You can also improve radiation heat transfer. Radiation is important at high temperatures, and when you want to improve radiation you need to increase your surface emissivity. So in that case you can use, for example, oxidized surfaces or black surfaces. When you need extremely high heat transfer rate, you can use phase change. Typical examples are boiling and condensation, and in electronic cooling cases these heat pipes are very important. Here we have a summary table how we can increase heat transfer. If we can increase temperature difference, it has the strongest overall impact on heat transfer rate. Materials having higher thermal conductivity will improve conduction. Larger surface area will improve convection and radiation. Higher velocity improves convection and higher emissivity improves radiation. Phase change will give the maximum heat transfer rate. Next we have some examples from electronic cooling. When talking about electronic cooling, we can say that our goal is to reduce resistance at every step. We need to minimize thermal resistance, and it means that we should shorten the heat path from SIP to ambient, use fewer material layers, and improve contact quality between layers. As a rule of thumb, we can say that fixed interfaces first before adding any fans or bigger heat sinks. We can improve SIP to heat sink conduction by adding some material having very high thermal conductivity. For example, pads or glue. Use always thinnest possible layer. Eliminate air gaps. We can say that air in this kind of application is insulation material. So eliminate air gaps always. Ensure uniform mounting pressure also. When selecting high conductivity materials, we can say that copper is the best, but it's heavy. Aluminium has a smaller thermal conductivity, but it's light. So one design tip is that you use copper base and aluminium fins. You can add heat transfer by adding surface area. You can add fins. That means that you increase your surface area. But when you are adding fins, be very careful that you are not blocking your airflow. One way to increase heat transfer is to switch from natural convection to forced convection. You can add a fan, but be very careful that you are not rotating your hot air back to your box. When you have high heat flux or uneven heat sources, you can use heat pipes or vapor dampers to move the heat from one location to another location where you can remove it. These heat pipes and vapor dampers are based on phase change. That means that the heat transfer rate is very high. When you make your design, you need to remember that your circuit board is not only electrical wiring, it's also thermal spreader, thermal conductor, sometimes even the main heat sink. And remember also the ambient heat removal. You need to take care of ventilation of your environment. Keep this ambient temperature low enough. When should we use air cooling and when water cooling? We can say that when the power level is below 30 watts, we always use air, and that's because the heat flux is so low and it's typically simple conduction and natural convection is enough. In this case, the liquid means additional costs and leakage risk also. If the power of your unit is, let's say, from 30 to 150 watts, then you can use air cooling as a first alternative, especially if you have space enough to add fins or a fan. Then you can use air cool. But if your box is very small and your heat source is very local and you want to avoid noise, then the water cooling is better alternative. If the power level of the unit is very high, then you should always use liquid cooling, and that's because in that case the required airflow becomes impractical and typically junction temperatures skyrocket. As a rule of thumb, we can say that if the power of the unit is less than 30 watts, use always air cooling, and if the power is somewhere 30 up to 150 watts, think first air cooling, and if, for example, the noise is the most important fact, then you can use liquid cooling. If the power of the unit is over 150 watts, liquid cooling is preferred. And if the power of the unit is very high, let's say more than 400 watts, then liquid cooling is must. Here we have some examples. For example, this kind of module, which is typically used in these applications. The main problem is that air cooling alone is not enough to keep those junction temperatures at acceptable level. A good design solution is that we use copper base plate and we have liquid cooled cold plate under that copper plate, and we need to use also thermal grease to get good contacts, and we need to, of course, control that coolant flow and its inlet temperature. Another example is this kind of automotive inverter, and in this case the main requirement is that it needs to be extremely reliable, and of course we want that there are minimum number of parts and the assembly is easy. The good design solution is that we use aluminium chassis and we have liquid channels integrated into this house. Here we have an example of a small gate driver. Also in these cases the overheating can be a big problem, although the power is at level 1 to 2 watts. And the main reason is that there is not good connection to copper plate. We need to remember that also in this small application this connection is very important. In this application we have a circuit board having total loss around 20 to 30 watts, and typically in this kind of application the heat is generated very locally, and it means that junction temperatures can be a problem. And a good solution is that we have large enough copper plates and we spread this heat before it's removed to air. In this application we have a 500 watts inverter. In this kind of application we typically use aluminium extruded heat sink with vertical fins, and it's also important to have an axial fan to cool down this box and remove heat to environment. If you have a local heat source, There is one very good method to move that heat from this location to another location where you can remove it. That's heat pipe. Here we see the principle of a heat pipe. Heat pipe is based on phase change. It means that in this hot location the liquid inside heat pipe is vaporized, and in this other end where we are removing heat to environment, the vapor is condensed inside heat pipe. Heat pipe is a good solution in case when we have quite high load and we cannot use any kind of a big heat sink directly in that device. When you're using heat pipes, remember always to ensure the good connection at hot end. Use thermal grease or solder to have very good connection there. And one single heat pipe can typically remove around 20 to 40 watts. So if you have high load, you need many heat pipes. Next we have some examples from heating and ventilation. In this application we typically use some kind of coil heat transfer unit. We have liquid flow inside pipes and air is flowing through this unit. Typical challenges in these applications are dimensioning challenges. The heat transfer is related to temperature difference between liquid which is inside pipe and air which is going through this unit. And if this temperature difference is very small, the performance is poor, and we need to be very careful when we design. We need to calculate first what is our airflow and what temperature difference we will have. Also there are many challenges if these are big units. Then we need to guarantee that the airflow to this unit is even. Maybe we need some guide vanes between duct before this unit. Here are some guides how we can get more effective unit. One way to increase efficiency of this kind of coil heat transfer unit is that we add fins. Then we need to take into account that those fins will add pressure drop at air side, and also it will increase risk that we will have deposition there, and it's not so easy to clean that unit if there are fins. Here we have one example in which we have coil heat transfer unit in duct. Typically in this kind of cases we have duct enlargement, and be very careful in this kind of cases that you will have even velocity before this coil heat transfer unit. Maybe you need some guide vanes in this kind of cases. One good way is to carry out a CFD study to see how even our velocity profile is before this heat transfer unit. Here is another example in which we typically have some problems with deposition formation, and we need to keep those coils always clean. and regular cold cleaning is needed in many cases when we have some particles in our air or gas flow. One important question is, of course, this pipe inside heat transfer. If we have a refrigerant case, so when time is running, there typically are some leakage and some coolant is escaping, so we end up to undercharge situation, and then this efficiency will go down. One important question is, of course, this how our condenser unit is working. When you locate this condenser, be careful that the air is not recirculating, so you will have always very good behavior and performance in this unit. It's always good to have some measurements, for example, a temperature difference and pressure difference, and also for fan power, compressor power. Those can tell if there is, for example, deposition formation or other challenges in system. When you are designing this kind of a system, check at least these things so that you have taken into account in your design. Here we have some more examples. For example, here we see a dirty condenser. In this kind of case, the pressure drop will increase very rapidly, and it's good to mention in maintenance instructions how we should check this unit and how we should clean it out regularly. We need to take into account also local weather conditions. In many countries during summertime the outside temperature can be over 40 degrees C, so it will affect on the performance of our equipments. And in many countries we are facing icing problems, so we need to think how we design our coils, what are the fin spacings and so on. In this last section we have some examples of industrial heat exchangers. I want to raise up some important design rules, how we can improve heat transfer in these units. When we make a design, we need to keep in mind this heat transfer equation. Heat transfer rate is overall heat transfer coefficient times surface area times temperature difference. And this temperature difference is typically highest in this kind of counterflow heat exchangers compared to this kind of parallel units. If we want to increase the surface area, we can add fins. And when thinking about this heat transfer rate, remember always this heat transfer resistances. So it means in practice that we should use high conductivity materials like copper and aluminium instead of steel. One good way to improve heat transfer is to create more turbulence. In this kind of cell tube heat exchangers we can use baffles to guide this flow in a cell. We can use CFD tools to calculate the flow field at cell site, so we can find out if there are some very low velocity, even dead zones, so we can optimize the location for these bubbles. In industrial application we typically have this fouling problem. We need to think, do we need filtration before heat transfer units, and when we create maintenance instructions we need to point out the need for regular cleaning. This kind of fouling can decrease the performance of our heat transfer units even more than 50%. Let's take a couple of examples in which heat transfer was improved. In this example we have a shell tube heat exchanger, and the problem was that the refinery needed to cool down the oil and couldn't meet this duty. So the counterflow configuration has solved this problem, and there are also these baffles to increase turbulence, and moderate tube velocity to limit the fouling, and carbon steel tubes. In this example we see a plate heat exchanger. In cases when we have tight mechanical room and need for high efficiency, this kind of plate heat exchanger can be a very good solution. Typically it's much more compared to shell tube heat exchanger. But if your duct is large, remember always that the incoming airflow needs to be quite even, and you maybe need some guide vanes before this unit. In this example we need to cool down natural gas from 120 degrees C down to 60 degrees C. We used finned tubes heat exchanger, and we have here fans to increase air velocity, and if we have dust particles we need to select the spacing of those fins so that this cleanup is easy. In this example a chemical plant needed to condense vapor, and shell tube heat exchanger is a very good solution for this kind of application. We put vapor on shell side and cooling water inside tubes. Here is a summary how we should start selecting heat exchangers. If we have clean gases or clean liquids, this plate heat exchanger is often a good solution. It's a good solution also for cases in which we have a tight space. If we have pressurized liquids, then this shell and tube heat exchanger is the first alternative. I have made some videos in which I have been developing calculation methods for heat transfer cases. For example, in these videos, heat conduction simulation and slab cooling simulation, I have been calculating heat flux through a wall. I made also videos showing how ships stay cool, and video in which I was simulating radiation heat transfer, and video of forced convection simulation, and then natural convection, and fin effectiveness, and shell and tube heat exchangers. I will add links to comment section so you can take a look at these videos. If you want to see a video of a special heat transfer case, please leave a comment. Okay, that was all this time. Thank you for watching and see you. Bye bye.